Welcome back to CST432. This is Lab 1, First Assembly Program. In this lab, we look into how to write or develop a program for NxOS-Armdebug. Now, before we get started, we assume that you have already completed Lab 0, where the OS drivers, libraries and tools, the next tools and Eclipse IDE have been set up. Secondly, we also assume that an NxOS-Armdebug project already has been downloaded to your computer using the techniques shown in the Lab 0 video. Before we begin, let's take a look at the NxOS directory hierarchy. The NxOS project folder contains several subfolders where the top level directories contain old tools, documentation and support scripts. The source code is actually found inside the NxOS subdirectory of the project. For the purpose of writing our first assembly language program, we assume that we will start from a template existing in the system subdirectory called armskel. The armskel template is actually a skeleton program template that we will start from to be copied to the actual program subdirectory, and we will modify it to show to change the subdirectory name, to change the assembly source file name, as well as the make file or the sconscript file used by scons for the building of the output file for the RxC program. First of all, let's take a look at the armskel template. The armskel template contains, of course, at the beginning, the headers defining the copyright as well as other pertinent information regarding the file. Then we see in the highlighted section the include files which are used for armskel itself. We note that there is an interwork header file that's used for the defining of various routines. The scaffolding header file used for defining the various common routines used by all NxOS projects. And finally, the debugger header file used for enabling the debugging of the program inside the IDE. Next, we should ensure that the enable breakpoints directive is defined so that the compiler or assembler will compile in the breakpoint support. Here we see a reference to an external routine, nxsysticwaitms, which is found in the NxOS base directory. As well, we have the define or equates for constant definition for various values that will be used in our routine. Next, we come to the data definition section. Here we have various strings that we use for display on the LCD when we want to look at the output of our program. The next section is for the definition of the code section. You see that code 32 indicates the ARM instructions will be assembled. .text indicates that it is a read-only section for storing code and other read-only data. And finally, align 4 will allow us to align the starting of the code section to an 8-byte boundary. As always, we define the entry point into the program main using a .global directive in order to show the linker that this can be called externally to this module. The first thing we do in armskel is to push the link register address so that we may return to the caller without any issues. This allows us to call subsequent subroutines safely. So the first thing we'll do is to call the NX program init to set up the system appropriately. Then we will also display a title on the screen to show that the program is running. Next, we encounter the debug breakpoint arm breakpoint, which is inserted into the code to force the program to enter into debug mode. Now, if we turn off debug enable or enable breakpoints, we would execute this instead, which basically is a delay loop to allow us to see the title being displayed on screen before the CPU does anything else. Next, we see a label called break. We define this label in order for the GDB clients to have a safe location to stop at, and we add a no op instruction here so that we will not trigger any unexpected side effects when the breakpoint is triggered. Finally, the main part of the armskel program. We have a loop counter, and we want to display a prompt, wait for 500 milliseconds, display some additional string, and wait another 1000 milliseconds or 1 second before we continue the loop. Here there is a fragment which is controlled by the conditional compilation statement if and if. So in this case, it's been turned off because the if value here is 0. To enable the looping in this program, we need to change the 0 to a 1, and this allows us to go through this iteration of displaying text on the screen several times up to the number given by the loop counter. At the end of the program, we want to shut down the CPU and other peripherals and return to the calling routine, which is basically to disable the CPU, turn off the next. So for this lab, we will prepare the first program by copying armskel to first in Eclipse, or else if you know how to use the command line in the terminal, you can also do it outside of Eclipse. We copy the armskel subdirectory to a new directory and rename it to first, which is used by the example here. Secondly, we also need to update the sconscript file to change the output RC file name to first. The next step is to define a new sconsolidated target in the Eclipse IDE so that we will build the first as the program using appskernel equals to first. The next step is to define a new external debugging target for this program by duplicating the armskel external debugging target defined previously in lab 0 and updating the application to first_rc.elf, which is the target elf file that we are interested in. The final step in this process, of course, is to modify the program to make the changes for it to do what you want it to do. Now make sure you define enable breakpoints so that it is able to allow us to debug the program using the IDE. After all the changes are done, we will build the first program using sconsolidator. If we have the successful build, we can now download first.rxe to the next using next2 and run it on next. At that point, because we have enabled breakpoints, the manual breakpoint we inserted into code at the beginning of the program will trigger and wait for us to activate the debugger. The next step for us to perform is to launch the GDB debugger, whether within Eclipse using the external tool launcher or else outside in a separate command line window, but it is recommended that we do it on the command line because it is normally more stable compared to running it from within Eclipse. Sometimes the Eclipse external tool launcher can get stuck and you find that the debugger GDB server is not responsive. So after this has been launched, the next step of course is to debug the program. In Eclipse, we choose run debug history or else run configuration and select the entry for the first program, then do the debugging. Welcome to the setup of the first program. In Eclipse, first thing we do, we select the NxOS subdirectory. Inside there, we go to the systems subdirectory, which contains all the projects defined for Eclipse in NxOS. Next, we will select armskel, which is the template for our first program. Notice there are some existing compilation in the directory. The output files of the object files, we will clean up first. Say OK. Now we have a clean armskel directory. Then duplicate this. Copy, paste. We give it a new name first. So when we get into the first program subdirectory, we want to rename armskel to first. Okay, make sure that you have the .s suffix for an assembly language source file. Next, we change sconscript to change the output binary or executable name from armskel to first. Save it. Okay, saved. And now we can Open it up. Look at the source file. Take note of the include statements here. Make sure that we define enable breakpoints. These are the data variables that will be used for display on the LCD. You can change that if you like. So this is the main program. Initial part to configure the next break. Then it encounters the manual breakpoint defined here, and the program will wait in the debugger. When we run the debugger, you will run into this break label, and you will allow us to control the execution of the program from within the GDB client subsequently. This is the main loop of the program, which does some basic display of information on the screen, and finally the cleanup routine at the end of the program when we exit. Now we shall build the first program by first defining a new target. We say add kernels equal to first, and we will build it. If there's a successful compilation, we will see an first_rxe.elf as well as first.rxe. First RxE is used by the Next itself, so we will download it using Next Tools. Inside Next Explorer, we will select the download program. It's found in the NxOS-Armdebug subdirectory, NxOS, Systems, first.rxe. So it's downloaded to the Next already. Highlight it and run. At this point, you will have been running on the Next, and you see the first prompt on the screen. But then after that, because it encountered the breakpoint, it will actually stop processing until we can connect to it using the debugger. Here we will launch the external launcher for the GDB server process, and we will also define a new target for the debug session. Copy the existing armskel debug target, change the name. Now we need to update the executable, which uses the .elf for debugging purposes. It's only used for debugging, it's not running on the Next itself. So go into the directory, NxOS Systems, looking for first, select the first_rxe.elf. Everything else should be the same, apply, and we run the debugger. Here we switch to debug view perspective. And you see this new screen. The first thing we need to do is to pause execution of the program. This takes control and allow the GDB debugger client to see the current execution position. You see the little blue arrow indicating the highlighted text instruction, which is the move instruction. Okay, we can also look at the register values in the next window here. They are up to R15. Just change the size of the window to allow us to see everything at once. Okay, there's another session here. In this case, we want to launch the GDB server outside in the command line terminal window. So we'll enter into the Armdebug project, go into the scripts subdirectory and run arm-nextgdb server. In this case, you can see some output indicating that the communication with the next break is successful. Then we will debug again. And in our case, we already run it once, so we can use the history to select the previous run first. Okay, so we stop the running of the process. We see that it has stopped at the move R7 loop count instruction. We're going to add a breakpoint at the instruction down there. We can step through the program. Look at the changes in the register values. Here we are going to execute load R0 with a new value, which is highlighted in yellow once the instruction has been executed to indicate there's been a change. We can continue, resume, or else step resume execution, and this allows us to continue until the breakpoint. We need to pause the program again to see where it has stopped. It shows that we have stopped at the next breakpoint that we defined, and again we can resume, or use other instructions to step over or step into the subroutine. We're going to toggle another breakpoint after the branch and link so that we can skip over the stepping of this routine. Say pause again. It has completed execution of the previous subroutine and is now at the new instruction. Then finally we stop the debugging and terminate the program. That's all. As always, here are some references and URLs for the resources we use in this lab. The NxOS-Armdebug is available from GitHub. The BricsCC or Nix2 is available from the Bricks Command Center website. Finally, some references for Git, GNU, and the debugger are available online as well from the following URLs. That's all. See you next time.